may be different. But anyway, all of these algorithms are based on the same strategy, priority. The problem is what kind of the priority we are going to use. So first, we are going to start from the first come first serve through the multi-level feedback view. Here nowadays, there are new algorithms for the scheduling. Okay, depending on your operating system. So do not expect the operating system like the Windows 8.1 or the iOS. Okay, even your small device has this one has some of the small device has their own operating system, embedded operating system. If that one is running only the process like the DOS level, you don't need the scheduling algorithm. Sometimes you need the long-term scheduler. Also, if you allow the so at that time, each operating system use the specific domain specific such as scheduling algorithm. But these are the general reference, well known and popular the scheduling algorithm. First one is the first come first serve. To understand, to evaluate the algorithm, we are going to use such a process information. When you see this list of process name, okay, arrival time, okay, this is arrival time 0, 1, 2 means first process 1 followed by process 2 followed by process 3, okay, and burst time means to be complete this process. How long? So let's say the time is unit the second. That means 24 seconds needed. Okay? And this one 3 seconds needed. This one 3 seconds needed. Okay? So then you can understand the process state. So we are going to use the similar or sometimes depending on the algorithm we will use different state. So also to make the problem easier, so we are going to use such a diagram which is called Gantt chart. Gantt chart is this one is the time from 0 to n. Okay? There's no meaning the width. Okay? So then we can specify. Sometimes it can use only just a line from 0 and P1 and P2, something like that. Doesn't matter. This is a Gantt chart. So first come first serve. At this time, I strongly suggest when you practice the CPU scheduling algorithm, first come first serve, definitely easy. There might be no problem to understand intuitively. But later, when we learn the other CPU scheduling algorithm, sometimes not enough for me. My brain is not that smart to understand at once all the state. I strongly suggest to use the ready queue. Okay? Ready queue. It can be this side or whatever that is, or something this kind of the queue, whatever. So why don't you manage your ready queue over here? So and also time. And time 0. P1 is alive. Okay? With the CPU burst time 24. Okay? Then the new process in the ready queue, so we can whenever the ready queue is changing, we can activate the dispatcher. And then our priority is arrival time. So dispatcher will select the one process from the ready queue. Definitely P1 will be selected. So P1. Then there might be two options. Whether we can stop in the middle. Okay? It's a preemptive or continue. But here, first come first serve, we do even though we start in time 1, P2 alive, okay, with the CPU burst time 3, our priority is the arrival time. Always P1 will be selected, right? So in the first come first serve, we don't have to run the dispatcher again. Okay? Once it is selected, it will be completed, terminated, because of the nature, due to the nature of the first come first serve. Because it considers always arrival time. Okay? So at time T1, if P1 is selected, we take the CPU resource during the CPU burst time 24. Okay? And time 1, P2 alive, and time 2, P3 alive with the CPU burst time 3. That will last until 24. P1 is completed. Next, P2. P2 is alive time 1. Okay? So this is earlier. So P2 will be selected. And P3. That is the first come first serve. So one of the easiest algorithm to understand. So we need to evaluate this algorithm. How can we evaluate? Using this one, criteria. So we are going to use mostly waiting time, okay, or waiting time and the response time. So first, waiting time. What is the waiting time of the P1? 0, because it started right away. What is the waiting time of the P2? It starts 24, alive 1, so 23. What is the waiting time of P3? Alive 27, it's still 27, and alive 2, 25. So average waiting time of these three is 0 plus 23 plus 25 divided by 3. So that is 16. What about the average response time? So response time is the first response time. It's the same as starting time, right? So that is the same as this one. Waiting time and response time is the same in first come first serve. Okay? So that is the first come first serve. Benefit? What is the strength of this algorithm?
Easy.
Easy, simple. Okay? It's simple to implement. Is there any complicated algorithm? No. It's just a select first come first serve. Okay? It doesn't have to even retrieve the process. Just from the queue, just pick up the first one. That's it. Problem. 5. Go ahead. Waiting time is increased. Why? Short amount time of process. Short, let's say that is a short process. Short process usually hidden by long running process. That is the problem. If we can execute first this one, we can reduce the waiting time. Also, we can reduce the response time. So that is the problem. So this is another example of the first come first serve, but for different order of the process. You can see here P2 arrived 0, P3 arrived 1, and P1 arrived 2. So obviously P2, P3 followed by P1. It's the same amount of the time, okay, CPU burst time, but different order. What is the average waiting time? It's just 2. It's a huge difference, 16 and 2, by changing the order. Okay? So that is the problem of the first come first serve. That is called the convoy effect. So usually short process, short running process hidden by the long running process. How can we address that problem? That's the question.
I was just calculating how is it 2, the average waiting time is 2 seconds.
How can we compute?
Yeah.
So,
it's the same way, but how does it turn out to be 2 seconds on?
so for example, P1 alive time 2, right?
Yes.
It's executed time 6.
6.
So 6 minus 2 is a 4, right?
Right.
And P2 arrived 0, execute 0, waiting time 0. And P3 execute the time 3, arrived time 1, 2 seconds. So total 6 divided by 3 is a 2. Okay? We just changed the order, arrival time.
So it also suggests that the process that takes longer time should be pushed at the back.
Yes. Then how can we implement that?
How can it
How can we address that problem of the conveyor effect? At that time, that is the shortest job first. We don't care arrival time, just care about CPU burst time. We'd like to run the shorter job first. So that is the shortest the job first. So first come first serve is a simple, very fast selection because if we have the queue, we don't have to retrieve the data. Just pick up the first one. Okay, even it's a bigger notation, it's just 1. It doesn't have to be n. Okay, because you don't have to retrieve the data. Just the bigger notation is 1. Okay, problem we already discussed about it. Definitely, this kind of approach is not suitable for the time sharing. So, how can we address the problem? We consider the remaining job. So that is called the shortest job. Not remaining, shortest job first. As I gave you the example, so if some of the students just need my signature, then whenever they are coming, I give the signature, then take care of the other student for long discussion. Okay, let's take a look at the example. This is a process list. We have the 4 process, and the process 1 arrived at time 0 and need 7 CPU burst time. From now on, even though it's not mentioned, sometimes I use the second for the unit, which is not practical, but for your convenience, I'm using the 7 seconds, something like that. Okay, but don't be confused. In real system, it's much less than the 7 seconds. It's usually the millisecond and like that. So 0 is need the 7. P2, so arrival time is 2. 4, arrival time 4 with CPU burst time 1. P4, 4. Okay. You can imagine the 2 different cases. What if somebody already meet the me for the discussion? So if there is another student who need my signature, can I stop the current discussion or not? So if we allow stop the discussion, then give the signature for another student and come back again, that is called the preemptive. Okay, it can be backup, it can be the guarantee the next time, not guarantee, it can be reserved for the rest time. So it can stop, then resume again. So that is one option. Second option is, so I don't stop the current process. As long as the process start to use the CPU time, it will be terminated. Okay? Then next time, among the student, when I select the next one, at that time I will consider the CPU burst time. Okay, only. So first we are going to consider non-preemptive case. Non-preemptive means it's not stopped. Okay, the current process should be terminated. Okay, that is the first option. So as I said, you do better manage the ready queue. That's a good idea. So I'd like to use this ready queue. The P1 is alive, the time 0, CPU burst time 7. Currently it's time 0. So 0, P1 is started. So P1 will be guaranteed to be terminated, which means it will take the 7 CPU time. Okay? And meanwhile, the time 2 P2 is alive. Okay? And CPU burst time 4. And also P3 is alive, time 4. P4 is alive, time 5. And with the CPU burst time 4. At this time, time 7, P1 is terminated. So this is time 7. Okay? Then, among these three, ready queue, which one will be the next one? We will consider only the CPU burst time. The first come first serve, we consider this one, but sure it's the job first, we will consider CPU burst time. So this one will be selected. So P1 will take the 1 CPU time, so time 8, it will be completed. We have two processes in the ready queue. For the tiebreaker, we can use the first come first serve. Okay? It doesn't matter because they are exactly same, identical in terms of the priority. So for the tiebreaker, we will use the first come first serve. So P2 will be selected, then next P4 will be the next one. Okay? This is the shortest job first in case of non-preemptive. Non-preemptive means we are not going to stop. Once the current process should be terminated. Okay, so we are going to compute the average waiting time. So P1 is the CPU burst time. Arrival time is 0. It's started 0. So waiting time is 0. P2 is the time 8. Arrival time is 2. 6. P3 is a time 7. Arrival time is a 4. And P4 is a 12. Arrival time 5. 7. So average waiting time 0 plus 6 plus 3 plus 7 divided by 4, that is 4. Okay? So this is a waiting time.
So for process P2 we have time 8, not 7.
Which one? Process 3?
Yes.
Process 3 executed time 7. It arrived time 2. Time 4. How long it wait? 3 seconds. So 3 seconds. Process 2 executed time 8, arrived time 2. So 8 minus 2 is a 6 waiting time. Okay?
No,
So on average it's a 4.
when we say arrive, which time is it? When arrive?
Arrive time is given.
No, but the arrive time is the time that it arrived in the ready queue.
Ready to yes.
And the execution time is which time?
It's a selected time. Selected by the scheduler.
No, because if you change the number 0, the answer will change, right?
Which one?
I mean, on the way, on your calculation.
Here?
Yeah. I mean,
Yeah,
if you
0
put
is
P3
0.
If you put P3 before P2, won't
Yeah.
it change the answer?
The P3 is the executed time 7, right?
Yes.
And it's alive time 4. 7 minus 4 is it wait. Process 3 wait the 3 seconds.
So we can't follow that table. We have to follow this.
Oh yes, both of them actually. This is a given state, process state. Okay, this is your Gantt chart for managing the schedule.
So for us to calculate the waiting time, we have to follow the Gantt chart, right?
Oh yes, But you don't know, using the Gantt chart, you don't know when the process is alive. Yes. So this is the waiting time of shortest job first. But this is a non-preemptive case. Another option is, why don't we stop the current process whenever new process is alive? Okay? So that is the preemptive. So the next one is,
Professor, one question.
yes,
What's going to be the response time?
response time.
Is it going to be the same?
Response time will be same. Why? It's just the first response. Okay? So it's the same as the execution time, waiting time. So response time of this one is the same as this. Okay? Because it's not, once it's started, it will be terminated. It's the same as the waiting time. Okay? But preemptive case may be different. We will see the preemptive. Preemptive case is the same process state as the previous one. So this is my ready queue. Okay. At time 0, P1 is alive. Arrival time is 0. CPU burst time is 7. So it will be selected. Okay. At time 2, P2 is alive. With the arrival time is 2, CPU burst time 4. At that time we stop. Okay? Current process. That is the main difference. Okay? So preemptive can stop the current process. So at this time, the CPU scheduler will select the next process. Next process is which one is the shortest CPU burst time? 7 or 4? Which one is the shorter job? Second, 4, right? So P2 is selected. Okay, at that time, what is the remainder?
5.
5. Because P1 used 2 CPU time. Okay, then time, so we, up to this one, time 4. P3 is alive. Time 4, CPU burst time is 1. Okay, then P2 actually selected, actually moved to the running queue. So we need to remove and go back. Okay, but I simplify this. Then P2 is a stop, remainder is 2. So we are going to consider 7, 4, 1 for the next process. Which one is the shortest job? P3. P3 remain, not remainder, so just the CPU burst time. Yes.
Professor, shouldn't we consider the remaining time?
That is the next average. Okay? That's the remaining job first. Okay? That makes sense. So before that, we consider only the CPU burst time. So 1. So P3 is selected. Then at time 4, P4 is alive with the CPU burst time. But anyway, this one is terminated. Okay? We don't have to consider. It's terminated. Running queue, then terminate. It's done. So we don't need this one. So among 3, which one is the next one? They are the same CPU burst time. We consider first come first serve as a tiebreaker. Okay? It's general decision. If you have your own tiebreaker, it's up to you. But in our class, we will consider first come first serve as a tiebreaker. So P2 is selected and it will be terminated because it remains only 2 CPU burst time. So time 7, so we have only 2 processes in the queue. 7 or 4, which one will be selected? The 4. It's a smaller job. So P4 is selected and take the 4 CPU time and the other P1 5. So it's done. We do not have any other process here. So P1 waiting time. P1 waited how long?
0.
Zero?
0 for the first part.
This amount of time. 11 minus 2. Right? It's a waiting time. Okay, total amount of waiting time. So P2. P2 arrived to and execute here and terminate here. So wait 5 minus 4. 1. And P3. P3 arrived time 4, terminate, no waiting time. Okay? And P4 arrived time 5 and executed time 7. 7 minus 5 is a 2. So 9 plus 1 plus 2, 12 is a 3. It's better, right? Preemptive case is better than non-preemptive case. What about the response time?
For
Response time, this is a waiting time, this is a response time. Response time, we consider only first response. Okay? P1, what is the response time of the P1?
0.
0. It's not 9. We don't consider the other. That is the response time. That's the main difference between response time and waiting time. What about the P2?
2.
P2, 2, 2. This is 0. What about P3? It's definitely 0. Right? And P4 is alive time 5, response,
True.
first time 7 is a 2. So it's a 2.5. Very good for response time.
but how do we calculate P2 waiting time?
Waiting time,
Yeah.
P2
It was initially executed at 2, right?
alive the time 2, right?
Yes.
And the P2 terminate this time, right? And between 4 and 5, it's just a waiting time. So it's a 1 waiting time. 1. Okay. Any question? You realize the difference between preemptive and non-preemptive, even through the evaluation criteria. So, evaluation using the evaluation criteria is very nice in terms of response time. Okay? Any question? Yes.
Why didn't we choose P3 before P2? Because it's
P3.
the shortest one.
When we select the this time, the time for how many processes we have? 3 processes in the queue, right? Which one is the shortest job?
Oh, in case of arrival time? Oh, it
Not
should be
arrival
P3.
time.
It is P3.
Yeah, P3. We just consider total CPU burst time. Okay? That is the shortest job first. However, as he suggests, why don't we consider remaining time? Okay? So if we consider CPU burst time only, it's always the 7, 7, 7, 7, right? Even though it is reduced, it is already executed. So shortest job first, do not consider the dynamically remaining the size. So if we consider remaining job, that is we have the remaining job somewhere. I don't think we have the slide for the remaining job. Anyway. So, if we consider such a remaining job, that is the shortest remaining job first. Why don't we calculate the remaining job? So, shortest remaining job first. So, shortest remaining job first with this one. So, we have on the chart, it's a 0, 5, 10, 15, 20. Okay, first in my ready queue, we have the time t 0, we have P1. P1 arrival time is 0, and CPU burst time is 7, remaining time is 7, right? This time P1 will be selected. Until when?
What?
Until when?
Until P2 arrives.
Until P2 next process is alive. Okay, so it's a time to it's alive to P2, and remaining job is 5, and it's alive to time 2. CPU burst time is 4. It's the remaining job is 4. What is the which one will be selected?
P2.
P
P2.
P2, because 4 is the smallest job. So P2 is selected. Okay. Then until when?
P3 arrives.
P3 is alive to time 4, CPU burst time 1, and this is a time 4. This one will be remainder 2, and this one is remaining 1. So P3 will be selected. And it needs only 1. So it will be terminated time 5. Okay? At time 5, P4 is alive. And CPU burst time 4 is a 4. Why don't you do the next one? And try. Bring your scratch paper. Complete the remaining of this one. Okay? Calculate the average waiting time.
So we will
And submit to the GA before you leave. With your ID. It will be another attendance check.
So what can you do?
So it's the remaining job. Okay. I will give the 5 minutes. Complete the Gantt chart and the waiting time. If you listen to my lecture, it will be very easy. You understand? Calculate the waiting time on it. The most important part is your ID. Complete the remaining of the Gantt chart of the shortest remaining job first. Okay? However, if you understand the question, it's very simple. Then calculate the waiting time, average waiting time.